This is Tomoyuki Chiba from UC Santa Barbara. Let me introduce today's speaker, Mihai. Mihai Sîrbu is a professor in the Department of Mathematics at the University of Texas, Austin. His research areas are stochastic control and games and the applications to finance and financial economics. Among his contributions to financial mathematics at SIAM, he is an associate editor of SciFin and has served on the SIAG FME Junior Prize Committee. He'll be talking about backward Martingale transport and Fitzpatrick functions in pseudo-Euclidean spaces. Mihai, please, screen is yours.
Okay, yeah. Thank you, Tomoyuki, for the invitation and the introduction, and thanks to the whole SIAM Math Finance group. It's good to see everybody. So I'm going to be talking mostly about a mathematical problem today, but this is I'm going to motivate it to explain what motivates the problem and what is a plan kind of to go ahead. Okay, so I think please, whenever you have questions, so please feel free to interrupt me during the talk. I think it's, or depending, or let Tomoyuki know and he will decide. But as far as I'm concerned, please ask me whenever it's a proper time. Okay, so I'm going to start talking about an equilibrium problem with an insider trading, and then the first version of this backward Martingale problem introduced by Kramkov and Xu in a paper in 22. And then I'm going to talk about the mathematics of what we have been doing, like the backward Martingale transport in more general pseudo-Euclidean spaces, and basically how they relate to Fitzpatrick function and projection in non-Euclidean spaces. And then I'm going to say a few words about the singularities of these Fitzpatrick functions, which are related to the existence and the uniqueness of optimal maps, actually existence of optimal maps and uniqueness of optimal plans. Okay, so let me start. I can see. Okay. Oh, sorry. Yeah. Okay. So let me start by describing the 1985 model of Rocher and Villa of insider trading. So it's in some sense, it's a very simple insider model, but it's very rich in terms of mathematical behavior. This is a variant of the famous model of Kyle with a different information structure. So there is an asset price or a stock which is going to have value capital V at time 1. And its price at time t0 is going to realize through an interaction between an insider, a market maker, and a noise trader. And the noise trader, completely uninformed, is going to post an order of size U, and the input of this problem is kind of like the random variable UV, or actually the law of UV. So, and now it depends from whom we are talking about. Like the input for the insider, so the insider knows at time 0, both the future value, that's the reason why it's an insider, but it's a very strong insider, knows even the order, the size of the order for the noise trader. And, sorry. So based on the information, so the insider sees capital V, and capital U. So for the insider, the randomness is completely resolved. And the insider is going to post an order of size measurable function G of capital U and V. Let's call it Q. Of course, for the market maker, this Q is going to be random. However, the market maker is not going to observe the Q, but is going to observe the total order, because the insider and the noise trader, they put the orders together. So the market maker is going to observe the total order R, which is Q plus U. So in this model, there is V, there is U. So price at time 1 order of noise traders U, insider observes both, and is going to post an additional order of Q. And the only thing that the market maker observed here is the total order R, which is Q plus U. And market maker has a pricing curve. So basically, when market maker, when observes price little r, is going to post through this curve f of little p, p is equal f of little r price. So market maker observed this realization capital R as a randomness, yeah, what it sees, but and it's gonna post therefore a price capital P, which is a function of capital R. Now, what is an equilibrium in this model is an equilibrium in this model is going to be something which is the equilibrium in this model, it's a pair of decision maps. So the G is the decision of the insider. So again, the insider for every little u and every little v is going to post an order Q. So of course, when these are realized, Q is going to be random, and that's going to be observed together with the U, making up the capital R by the market maker. And another choice of a pricing curve F for the market maker. Yeah. So the Roche-Villa equilibrium says, oh, an equilibrium, it's a choice of two things. G, the rule of the insider, and F, the pricing curve of the market maker. And they're going in such a way that given the pricing curve, the strategy is going to be optimal for the insider. In other words, the insider, given the pricing curve, is going to have, in this case, a completely deterministic maximization problem. So the insider is going to buy or sell post an order Q, and at the price F of the total order, Q plus U, this is the total order. And this is how much the market maker is going to post. And at time, terminal time is going to be worth V, and it's going to be Q of them. So this is going to be the profit of the insider. So given the pricing curve, the profit of the insider, realizing the profit of the insider is a deterministic optimization problem. And this is how G is going to be used if F is known. On the other hand, an equilibrium is going to be in that these F and G's, they are in such a way chosen such that the price is efficient in the following sense. The information that the market maker has is just R, which is Q plus U, so the total order. So Q is the order posted by the insider, U is the order posted by the noise trader. So that's the only thing that the market maker is going to observe. And of course, given F, given little g and given F, that's going to be random depending on U and depending on the realization of U and V. And now in equilibrium, the price should be efficient. So the price should be a martingale, So in other words, based on the information now, which is R, the price that is posted in equilibrium should be the conditional expectation of the future price. And actually turns out, because P is a function of R, it's the same thing as conditioning just on the price itself. So let me say one more time, the only information there is a question whether this is an inconspicuous trading property. So in what sense? So in order to
so the last equality R is equal to expectation of U conditional to R.
Yeah. So this is a part of the definition of equilibrium. Yeah.
Okay.
Yeah. So I believe so. I would need to double check the terminology, the economic terminology. So from to be able to answer a yes or no, so this property is posted as a definition of the equilibrium. Yeah. So in some sense, yeah. So yes, it's efficiency or yeah, inconspicuous. But so I know it under the name of efficient, but I would have to check the names. So yeah.
So just to precise, the last equality, R is equal to expectation U given R. So this means that the market maker doesn't see the order of noise trade.
Yeah. So I was answering a different question. So the last question. So yes, basically that's what it means, that based on the information, so the total order and the order of the noise trader, they're also in Martingale property. But this is not a part of the definition of equilibrium. This is a part of the solution, and in some sense, and the answer is yes.
It's an outcome. Okay, thank you.
Yeah. So thank you. So I apologize. I was answering a different question, and the answer is yes. So basically, as a part of the definition of the equilibrium, only prices are in Martingale property. But it turns out that as a part of the solution, that also the orders are in Martingale property, and this is in many ways it's a very important property. Yeah. So basically, based on the information, if things are efficient from the point of view of a price, then it also is going to say that, oh, based on the information now, this is the best guess for the total for the order of the noise trader. So based on the total order, this is exactly the best guess, like conditional expectation for the order of the noise trader, which is not seen by the market maker. Yeah. Thank you. So now, okay. So please let me know if you have more questions. I really appreciate them, and sorry that I kind of misunderstood the question to begin with. Okay, so let's take this equation that was mentioned, which is particularly important. So again, as a part of the definition, prices are in Martingale properties. As a part of the solutions given by Rocher and Villa, it turns out that also orders are in Martingale property. And this idea was reformulated by Kramkov and Sîrbu in the following way. We can denote X like total order let's say in equilibrium in this case, and total price, that's a vector, 2D vector, and Y is going to be like a column vector, not necessarily a row, UV. So these X and Y are in Martingale property because the truth is, in this case, the information in X, so P is a function of R, so it's exactly the information of R. That's quite important, but yeah, this is going to show up later when we want to reverse engineer the problem. And the idea and the insight from Kramkov and Sîrbu by introducing the backward Martingale problem is the following. One can pose the problem as an equilibrium, or instead, look at all the X and Y, we are in Martingale relation to, so look at all X equal RP, which is in Martingale relation with a terminal UV, and then optimize the problem like in conditional expectation, optimize R minus U times V minus P over all these choices of the Martingale maps. X is a function of Y. So it's certainly not obvious, but it turns out that these two problems are somewhat equivalent, subject to, of course, some technical conditions. So now, so this is kind of the key insight. Reformulate the equilibrium problem as a backward, like a transport Martingale problem. So optimize, so fix Y, optimize over all X's, which from X to Y, I'm going to move as a Martingale. And take the expectation R minus U. So this is basically what would be the order of the insider. V minus P is a price increment, and optimize it. And it turns out that if we separate through the Martingale property, we're going to have this kind of 1/2 expected value RV plus PU. And for the matrix, which has entry 0, 1, 1, 0, actually, these things that we are optimizing is nothing else than the scalar product between x and sy in expectation. And of course, uv, these are given, so this expectation is going to be constant. It's not going to change anything. So that's the key insight from the work of Kramkov and Shu. One can attempt to reformulate an equilibrium problem, taking into account the last equation that was just described, which is a part of the solution. It's expected to be a part of the solution. One can reformulate it as a true backward Martingale problem 2D. So when y, which is uv, it's mapped into x as a map. And indeed, it turns out that they have a theorem saying that, oh, there exists a solution to the equilibrium problem, where again, the equilibrium is posed as a Martingale problem only for prices. The rest is going to be a part of the solution. If and only if there is an optimal map for this Martingale problem, which solves the backward Martingale problem. And in this case, we have exactly the relations like in equilibrium, Q, which is going Q, the order of the insider is going to be exactly U minus R, and it turns out that this optimal solution, like R and P, will lie on a graph F is equal F and R, where actually F is increasing. So solving one problem is basically equivalent to solving the other, but again with a but, as long as there is a map solution to this problem. Of course, I did not say what a map is or a plan, and of course that's going to be a part of what I'm going to do next in a slightly more general case. Okay, so my hope is that this kind of motivates the mathematics that's going to come. So there is the equilibrium problem with insider, where insider knows not only the price, capital V, but only the full order, the exact size of the order for the noise trader, problem of Roche and Villa. This is formulated as a backward Martingale problem, and subject to technical conditions and existence of maps, it's a kind of an if and only if, and one translates into the other. So what I want to present today is kind of how to study some more general backward Martingale problems. Of course, the motivation is application. So what we have in mind is equilibrium problems, pretty much like this, but even in higher dimensions, like the mathematics, is kind of difficult to do it precisely. And also other kinds of applications, like, for example, the idea of principal curve, which is a nonlinear principal component analysis of Hastie and Stutzle, in some sense translates in a pseudo-Euclidean case as a backward Martingale transfer. So we have like several applications in mind, but I'm going to focus today mostly on the mathematics. So I'll present the problem and explain how optimal planes or optimal plans relate to pseudo-Euclidean projections and what is called Fitzpatrick functions. I'm going to talk a little bit about the geometry of singular sets for Fitzpatrick functions, and this is exactly the ingredient that is needed in order to obtain optimal maps. So this is not posted yet, but it's forthcoming pretty soon. Okay, so as I said, going to be a more general problem. So we work on the so-called S space. So in D dimensions, we look at all the symmetric matrices which are non-singular, and they are going to have M strictly positive eigenvalues and obviously D minus M strictly negative eigenvalues. This is going to be the bilinear form, like S of X and Y is a scalar product between X and Sy. This is going to replace from 2D, is going to be replace the matrix. So in 2D we have the 0, 1, 1, 0. We're moving to D dimension and we take more general structures than 0, 1, 1, 0. Okay. And this structure defines a pseudo-Euclidean structure. We call it RDM. And it has dimension D, dimension of the space, and index M. So this is basic. M is the number of strictly positive eigenvalues. And S of X scalar product with itself, it has a meaning of the norm. We call it scalar square. of course, it can be negative. So basically, distances and square norms can be negative in this space. Okay. In this space, we're going to pose the Martingale problem in this way. Fix a y, d-dimensional, that's a random variable which is fixed, and maximize this kind of quadratic structure, expected value as xy, over all the random variable x, which have their maps. So they are maps of y, exactly what we need for equilibrium. Sorry, I apologize. Things are moving on my screen. So we look at all the maps, x is equal f of y, which also have Martingale properties. So based on the information in x, which is a map of y, x is exactly the conditional expectation of the later y condition on x. And for all of these maps, we want to maximize this kind of quadratic structure as xy in expectation. And this is a backward Martingale problem based on the S structure. And again, so a map is going to be a Borel function of y. Now, I'm going to start with a linear example, which is it's an interesting exercise with matrices. So we assume that y is a Gaussian random variable with mean 0 and covariance matrix sigma. So recall, so as the pseudo-Euclidean structure is fixed. So we have a theorem that there exists a unique decomposition of the covariance as a Q plus R, where these matrices Q and R, they are both symmetric, both positive, but not strictly positive. And Q as Q is positive, R as R is actually negative, and Q as R is 0. So we have a matrix decomposition on sigma with respect to this kind of pseudo-scalar product given by S. Now, what this matrix decomposition tells us about the our problem is the following. We can take the original random variable y, so this is Gaussian mean 0 with covariance matrix sigma, and we can decompose it in an x plus z, where x is going to lie on a hyperplane which is positive with respect to the S structure. So this is what it means. Sxx is greater than 0. So x is random, so this means almost everywhere. So the support of this x, we're going to split to decompose a Gaussian in two independent parts. One is going to lie on a positive S space, the other is going to lie on a negative S space, and the two spaces, their spaces are going to be orthogonal with respect to the S structure. And actually, it turns out that there is a direct relation between matrix decomposition and this Gaussian decomposition. So basically, Q is going to be the covariance structure of the first part. So of course, it's going to be supported on the positive hyperplane. R is going to be the covariance structure of Z, and the correlation is going to be 0. Yeah, this comes from independent. Let's note that Q has rank M. This is a number of positive eigenvalues. It's a part of the solution. And R has rank D minus M. So actually, going a little bit further with the kind of notations that I was just saying, if I denote by G the support of X, so it's a hyperplane, this is where this Gaussian random variable lies, and by H the support of Z. So this is what we're going to say, that really we're decomposing RD in two hyperplanes. G has dimension M, H has dimension D minus M. G is S positive, H is S negative, hyperplane, and they are S orthogonal. And this decomposition is unique. And furthermore, X is actually going to be the projection of Y onto the original, onto the positive hyperplane. Yeah. So if we denote by P is equal to Q sigma inverse, really, it turns out that X is a projection of Y onto G. And what does it have to do with our original problem? This decomposition, why it's decomposed into X is equal, Y is equal X plus Z. X is a projection of Y on a positive hyperplane. I'm sorry. And this projection is actually, which is linear, is the unique optimal map for the backward Martingale problem. So we can solve the problem of backward Martingale problem in this Gaussian case. So we have this kind of observation that, again, if G is the range of this projection, which is always the same as the range of the projection P, it's the same as the support of the X. Yeah. So if G is a hyperplane where X lies, then G being a hyperplane and being monotone and being positive actually means, if we write it, it means that any two elements in X in G, they're going to be in this relation as XY is going to be positive. And it turns out basically because of dimensionality in this case, this is the largest set with this property. So there is no point outside of G which is going to be in positive relation with an X, with all the X's in G. So morally speaking, the G is an S maximal monotone set, this hyperplane where X is supported and over which we project to find the unique optimal map. And the matrix P, which it transforms, so X is equal P times Y, is actually the projection matrix on this hyperplane G in the S space. In other words, P is an argmean. So for each Y, we take this pseudo-Euclidean distance from Y to the G, which is a linear space. And of course, because it's a linear space and has a quadratic structure, that's going to be also a linear operation. And this is a projection. So we can see from this linear discussion that in the Gaussian case, we can expect the solution to be to project on a linear. So in the Gaussian case, which is linear, the solution is to project on a linear maximal monotone set S. And in some sense, the general case, it's going to be pretty much like a generalization to a nonlinear case if done carefully. Okay, so in order to go to the more general case, so let me introduce the definition of backward Martingale plans. So again, a map is something that takes Y, maps it as a function of Y into an X, and X and Y are into martingales. Now, we allow for X and Y's, which are not necessarily, X is not a map of Y, but only have the martingale property. So basically, a plan has to be written at the level of laws. So we say that gamma is an optimal plan. Gamma is a martingale plan if it has a marginal on Y equal to nu. This is a law of capital Y. And it also has a martingale property. So by observing X, so this is the conditional expectation of Y condition on X. So we move now from maps to the relaxed problem of plans, which has a convex structure. Okay. So let me know, do you have any, if there are any questions? Yeah, so we have the problem of maps. That's the original problem of interest. In the linear case, we solve it. It's a Gaussian decomposition. And we notice this is a projection on a linear maximal monotone set G. It's a hyperplane going to 0, which is strictly positive. In the nonlinear case, we have to move in the first step, at least, to the relaxed problem of plans. So we don't look just at X is a function of Y. So we can look at laws, or if we enlarge the probability space, we can look at X and Y's, where X is in martingale relation to Y, but it's not necessarily a map F of Y. So that would be a martingale plan. Now, I'm going to skip a little bit. So the dual problem to this is going to be given over maximal monotone sets. So if you recall the linear case and the composition, so basically, so what we expect is one way or another, that at the end, we're going to have some projection like we had in the linear case on a maximal monotone set. And this is exactly how it will look, provided that we define an appropriate dual problem, and G is going to be solving exactly this dual problem. So we extend the definition of monotonicity and maximal monotonicity through nonlinear sets. So we say that G is S maximal monotone if any two elements in the set G are in, the difference is is going to make S X minus Y positive, and its maximal is if there is no other set which is monotone, which is going to strictly include it. And the dual problem is going to be an optimization over convex functions indexed by these maximal monotone sets. So, and this is exactly the set of Fitzpatrick functions. So fix a maximal monotone set G. Now, for which Y we take supremum over all G's like Sxy minus 1/2 Sxx. So in some sense, up to a small transformation, this is like the optimizing the cost of the insider. There is a little bit missing, but that's what it means. Yeah. And this convex function is called the Fitzpatrick function, and the dual problem is to minimize over all maximal monotone set G's the set of Fitzpatrick. The integral of the Fitzpatrick function with respect to the measure nu. So recall, nu is a law of Y. So in some sense, take Fitzpatrick functions corresponding to G's, plug capital Y inside, take expectation. And then this is going to be the minimal over all G's. It's basically the dual problem to the problem posed over martingale plans, backward martingale plans, not maps. So, morally speaking, what are these kind of Fitzpatrick functions? They are all the kind of, they are the minimal elements of the, so if we look at all the convex functions which lie above this quadratic obstacle 1/2 Sxx, which is not convex, yeah, because it has S has positive and negative eigenvalues, Fitzpatrick functions are really minimal elements of this set. Now, for the case when the space is Rm times Rm, so D is equal to M, and S is basically the generalization of the one-dimensional structure. So instead of having 0, 1, 1, 0, we have the identity matrix in M dimension, identity matrix in M dimension. Really, Fitzpatrick function and the concept of monotonicity, it's exactly what is called monotonicity in the analysis that involve kind of Hilbert spaces or over RD. So this would be the standard, I would say the standard form for S is when we have M negative eigenvalues. Oh, so minimal function in the sense of a pointwise ordering. So it doesn't say, so so basically, yep, so.
But it's not I mean, minimum of two convex function is not convex.
Yes, yeah. That is exactly the point, but doesn't say that there is a unique minimum. So this is exactly the problem. So basically, there are going to be chains of convex functions above, and each of them is going to have a minimal element lying above this. But it doesn't say that the minimum of two convex functions is convex. You're absolutely correct. That's exactly the point.
Okay.
So, because let me put it this way: if we take the envelope from below and we look and we take the supremum, we have only one element which dominates everything. Here we have a lot of minimal elements over this kind of chains in the sense of Zorn, basically. Does it answer the question?
Yes, thank you.
Yeah, so basically, so this is exactly what it says. So in some sense, for a Fitzpatrick function, there is no other convex function which is above the obstacle and is going to lie below. Or another way to say it, for every convex function above this obstacle, there is a Fitzpatrick function which is below, but above the obstacle. But of course, there is going to be a lot of Fitzpatrick functions. So basically, so this is what it says. For each G, which is a maximal monotone set G, we have a psi G, and we change G, we change this. And all of these are minimal in the sense of pointwise ordering, yeah? So thank you for the question, and I hope that I did answer, but in case I did not,
Thank you. Thank you.
please let me know, and I'll follow up. Okay, so I believe that I'm a bit slower than what the plan was. So I'm just going to describe like the standard form. The standard form really means that we have m negative eigenvalues, m positive eigenvalues, and actually the matrix S has a very specific structure, is 0, 1, 1, 0. So in other words, if X is UV, if we look at the quadratic form SUV applied to UV, it's basically 2 times scalar product between U and V. So this standard form is really how people, how in most cases monotonicity and maximal monotonicity, especially like is known, especially in the PDE theory and maximal monotone operator over Hilbert spaces. And this is kind of also the way Fitzpatrick introduced the function psi sub G in convex analysis, and then it was kind of generalized for more general quadratic forms. But this is what we call the standard form. This is S monotonicity is what people call monotonicity, and maximal monotonicity in Rm times Rm and Fitzpatrick function. So this would be the standard form. There is another example which is quite interesting. We can have canonical form like m negative eigenvalues, d minus m positive eigenvalues, but we put all the eigenvalues on the diagonals and zeros otherwise. So we have 1, 1, 1, minus 1, minus 1, minus 1, and all zeros. So really, if we look at basically lambda x, comma itself x, what we're going to have is the norm. If we split x in u and v, it's going to be u squared norm minus v squared. So it turns out that if we want a set to be monotone, actually a monotone set in this sense is going to be a graph of the form UFU when f is a 1 Lipschitz function. So if lambda is canonical, so m1's d minus m negative 1 on the main diagonal, if lambda is canonical, I'm sorry, then monotonicity means Lipschitz 1 property. Now, maximality means that we have a global function, because by the Kirth-Brown theory, a 1 Lipschitz function on a set can be extended to a 1 Lipschitz function everywhere. And if monotonicity is equivalent to Lipschitz, maximal monotonicity is going to be equivalent to a global Lipschitz function. So U is going to be defined everywhere. F is going to be defined for all the U's in Rm by Kirth-Brown. So we have this special case where monotonicity amounts to a Lipschitz property in a graph. So it turns out, using this trick, that actually, of course, every kind of S, we can do a linear transformation and transform it into a canonical case. So of course, we have to keep the number of negative, positive eigenvalues. So we can transform S. So we change coordinates such that S becomes canonical. Then whatever monotonicity was in the S structure is going to also be monotonicity in the lambda structure under this transformation. So in other words, what it tells us that actually maximal monotone sets, they are actually linear transformation through these V's of global graph of Lipschitz 1 function. So this is basically the equivalent of what is mean to representation called in the standard case 0 IM 0. So in a canonical coordinate. So really what it says is maximal monotone sets, they're linear transformation of Lipschitz graphs of dimension m from Rm to Rd minus m. So when something is maximal monotone, we know exactly what its dimension is, and its dimension is m. And m is the number of positive eigenvalues for this symmetric matrix S, which is kind of defining the Pseudo-Euclidean structure. Yeah. So basically, if I go back to something that I skipped a little bit, so if M is equal to D, that's what it says. There is only one maximal monotone set, the whole space. Yeah, because if M is equal to D means we have to put everything in here, otherwise this is not going to be maximal. Yeah. Okay. So now that we have the Pseudo-Euclidean structure S, and we have defined maximal monotone set G and the Fitzpatrick function. The Fitzpatrick function size our G, which is really a supremum. Okay, and I'm sorry, that's a sorry. This is correct. This is supremum over all X in G's. Yeah. If we rewrite this a little bit, it turns out that computing the Fitzpatrick function is actually the same as finding basically the points where Y is projected in this non-Euclidean pseudo-Euclidean structure on G. So we minimize. So computing the Fitzpatrick function is the same that for each Y, we minimize the pseudo-Euclideans from Y to all the Z's when Z lie in this maximal monotone set G. So from this observation, it turns out that this projection is nothing else than this subgradient of the Fitzpatrick function, yeah, inversed by S inverse intersected G. Okay, so I'm going to this is a picture showing how kind of geometrically pseudo-Euclidean projections differ from Euclidean projections. So in order to, so X is Euclidean projection of Z, so we have a tangent circle condition, but at the same time, X is a pseudo-Euclidean projections of Y1s and Y2 on different sides of G. So Euclidean projections are given by a tangent hyperbola condition, and the hyperbola is given by this exactly pseudo-Euclidean structure. So the main theorem now for the existence of, for studying the problem of plans is the following. We have the primal problem, supremum over plans, dual problem, infimum over maximal monotone set G. Fitzpatrick, so take maximal monotone set G, Fitzpatrick function psi is convex, and integrate against nu. Now, so it shows there is always an optimal plan, there is always an optimal G, and actually these two values are equal. And the more important thing is the following. We fix any Martingale plan and any maximal monotone set G. Then, if X is projected, if X is a projection on this maximal monotone set of Y, but let us remember that X and Y are in Martingale property. So if we have Martingale property between X and Y, and X is a projection, the pseudo-Euclidean projection of Y onto G, then this is an if and only if condition to conclude that X and Y, which is the realization of the log gamma capital X and Y, form an optimal plan, and that G is an optimal dual G. So again, we fix a plan and we fix a G, a Martingale plan, and we fix a G. If X is the projection on G of Y, then XY is an optimal plan and G is an optimal for the dual altogether. So this is exactly what I'm saying on the next page, that we take any solution G to the dual, and also now we take an optimal plan, then by exactly having the if and only if, this is what we can conclude that, oh, optimal plan, optimal dual, we know for sure that X is going to be the projection of y on G. And of course, so what does it mean? If this projection, so if each, we have to study what can happen for this projection to 1 point to go into more than 1 point. So I think it's a proper time to ask Tomoyuki, do I have 5 minutes or I have to stop now?
I think you have 5 minutes, please.
Okay, yeah, thank you. So we take an optimal plan and we take an optimal dual G. The if and only if characterization of optimal plans and optimal G tell that for this fixed optimal plan and fixed dual optimal G, X is a projection of Y onto G. So therefore, if I know that this projection is not going to be multi-valued, so of course any point can be projected into 1 point. This is nice regular points on into more points. If I know that there's going to be only one value here, that's not going to be a set but just a point, then life is going to be good. I'm going to have existence of maps and actually even uniqueness of plans. So really, because Y is transported into X along of this subgradient or the gradient of this Fitzpatrick function, what it means is the Fitzpatrick function psi sub G plays for us the role of the Kantorovich potential from the classical optimal transport. So, and the existence now of optimal maps and optimal plans are really related to the singularities of this projection. So basically, if I define the singularities of the projection to be those axes where the projection is not a single point, now what we want to do is to study the geometry of such singularities. And how does it work? Let me go this many slides back and say the following. PG, what it is really kind of the subgradient of the Fitzpatrick function. So the subgradient of the Fitzpatrick function, so Fitzpatrick is a convex function. So now, of course, the subgradient can be single valued, regular points, and can be multi-valued. This is singular point. Now, the singularities, like whether the projection has one or more points, is of course going to be exactly the same as whether the subgradient of this function psi g has one or more points. There is a theory from 1979 by Zajíček who says that singularities of convex functions, so basically all these points where subgradients are multi-valued, can be covered by countable C minus C surfaces. So by C minus C surfaces, we mean that we can separate one coordinate xj, and these can be written as a function of like a difference of two convex functions of the remaining ones. So one coordinate, it's a convex minus convex function of the remaining coordinates. So Zajíček showed that, all singularities of convex functions can be covered by countable C minus C surfaces of dimensions D minus 1s. What we can do, and to show, we can show that not only that we can cover singularities of Fitzpatrick function by these C minus C countable surfaces, we already knew that from Zajíček, we can show that we can choose these surfaces to have special geometry. So if we look at all the D minus 1 dimensional surfaces, C minus C, so one coordinate is a convex minus convex function of the other D minus 1 coordinates. And if we look at these surfaces to have normals in the direction of the S space, which are S positive. So in some sense, this is quite restrictive. So the normal cannot have any kind of orientation like in Zajíček, but we restrict it to be just S positive. These surfaces with this orientation, a countable number of them, is going to cover all our singularities. So in some sense, what it said is singularities of Fitzpatrick function, they are severely restricted compared to singularities of all the convex functions. And now that's in this paper that about singularities of Fitzpatrick functions and actually geometry of singularity of convex functions in general. And this is the main tool that we are using now to show exactly that, oh, there is going to be optimal maps under what conditions and so on. Okay, so I'm going to move to the summary and say, so what are we doing kind of mathematically? We have the S structure, pseudo-Euclidean, we fix a random variable y. Now, an optimal plan is realized by random variables x and y. So xy is an optimal plan if it's in Martingale relation, if and only if x is a projection of y onto some maximal monotone set G. And now, in order to make sure that we can have a map, and this is ultimately what we want, that X is a map, we need to make sure that, oh, where Y lies, PG is not going to have more than one value. In order to do this, we provide a geometric description for the covering of singularities, of singular points of PG, and singular points of PG are exactly those points where the projection can be multi-value. And now in the immediate future, we plan to apply this to the existence and uniqueness of optimal maps and obviously plan. Okay, so I think my time is up, and if you have further question, I am here.
Thank you very much, Mihai. Very nice.
Thank you, Tomoyuki.
Any questions from the audience?
So I can have one question. I mean, there is a part that I missed.
Yes.
When you pass, I mean, you have this some sort of duality, right? Where you show that this
Here?
one. Oh, yes, exactly. So when you say existence of function, it is essentially the fact that this minimum is achieved. Is this what it means?
Existence of which function?
So when you say at the end, optimal transport maps, right?
No. This shows just existence of plans.
Okay.
So this is about plans. So there is an optimal plan and there is an optimal dual. Yeah. And so this theorem, so basically the dual problem is dual to the relaxed problem of plans, because the problem over maps is not convex. So we can only do duality for convex problem. The problem over plans, this is convex. And this is what we show here. There is an optimal plan, there is an optimal dual G. And these guys are in relation that X belongs to the projection of Y over G. And now, thank you. So this is a very nice question. So again, if the optimal plan, we can see it realized by random variables X and Y, yeah, X is in Martingale relation with Y, that's what we have. Such a thing exists, there is an optimal dual G, and also X belongs to the projection of Y onto G. But now, if the projection is multi-valued, this may not be a map. That's exactly, we need the projection to be single value to have a true map. So does it answer the question?
Yes, thank you. That was clear.
Thank you. Yeah, this is kind of a very nice question. Yeah, that's kind of exactly the gist of it. Yeah, thank you. And this is exactly like, if Y is not going to take values where PG is multi-valued, then that's a map. But if Y is going to take values in places where the projection goes in multiple places, then maybe a plan is as good as it gets. Oh. Yeah. So basically, so we do duality for the convex problem, we solve it, and then in some lucky cases, you can show, oh, the solution of the convex problem, it actually belongs to a smaller class, which is not convex. And this is exactly why we need to study singularities of PG. Okay.
Any other questions? Can I ask a naive question?
Yeah.
In this problem, the number D, the dimension of the operators, plays some significant role. I think in the actual calculation, yes, but can you see any, like, my question is, can we say we solve for the problem for dimension D, and then can we update for the problem, similar problem for D+1? Is there any insight from this analysis between different dimensions?
So basically, it depends a lot on S, because when you move from one dimension to another, you choose a different S. And now the whole point is, so the key kind of the geometric things that describe the solution of the problem is not only S, but what is essential from S is how many positive eigenvalues that it has. So have D, this is a dimension, and M, it's kind of the index of this space. So D and M, these together. So basically, all maximal monotone sets are going to have dimension M, yeah, in space D. And now when we move from D to D+1, it depends what kind of S we choose, because we can choose an S which has M+1, or we can choose an S with the same M. So things kind of change.
I see.
So in some sense, yeah, I know how to reduce dimension below to restrict it, because we know what is a trace of S. But if we go above, it depends on what S we choose on a larger space.
I see. Thank you.
Thank you.
Hey, Mihai, I also have a question related to this. So this is a one-period model, right?
Yes.
Yeah. So if you do two periods in this type of model, you're going to get stochasticity, right? You're not going to have a purely deterministic problem for the insider. Right, because so I mean, I'm just wondering if you try the two-period model.
Yeah, no, we are looking at it. It's not done, but the answer is yes.
Okay.
Yeah, we are looking at it. Yeah, it's not here. Yeah. So no, so yeah, so things change because of course, if you have two period, like the insider is going to see this noise trader sequentially. The insider is going to know V, but is going to, of course, learn about the different noise traders sequentially. Yeah, so things are going to change. So mathematically, they change, I would say, quite significantly. Yeah.
And so if you can solve this two-period model where you have stochasticity in the insider's problem, so this is starting to look a little bit more like traditional Kyle, where in a one-period model you're going to have stochasticity in the insider's optimization problem.
So from this point of view, yes, but so yeah, but it's going in a so there is certainly going to be, so basically at time one, so at time 0, the insider is going to have a problem. So basically, they have a two period. At time 1, the insider knows what basically the second noise trader already did, but at time 0, it's not going to know that. So basically, this is going to be unknown. So in some sense, yes, there is less information. So from this point of view, the fact that the insider has some stochasticity, yes, it does look a little bit more like Kyle. So the answer, from the informational point of view, the answer is yes. The insider, like sequentially, is going, no, it doesn't have all the information in the beginning.